Welcome back to our last chapter. This is going to be chapter 14, taking a look at weather patterns and severe weather. So we have taken a very close look at the atmosphere in particular this last half of the semester. And so we're well equipped now to try to look at the various weather patterns and including some of the severe weather. And just kind of to get us started here, just to think about all of the types of kind of hazardous weather that we do have. We typically think of tornadoes, hurricanes, thunderstorms, floods, these sorts of things. And so I have some statistics here of weather fatalities. These are culminated for 2019. That's the latest we've got so far tallied. But what they've done here is put together, you may not be able to see all the details of the names and things on it, but for the year of 2019, weather fatalities, so NOAA puts this together, National Oceanic, Atmospheric and Oceanic Administration puts this together. And so they do this on a 10-year average, so say from 2010 to 2019, that's sort of the blue bar here, the blue bars, of each one of these. The yellow bars are averaged over 30 years because that's what meteorologists like to do, average things over 30 years. And so the yellow bars are for over 30 years from 1990 to 2019, and looked at some statistics. And of course the red bars are culminated for 2019. And so strikingly, we right off the bat see a 30-year average here, this yellow bar, for heat-related deaths. They tend to be the largest, but second to only to the heat. Might be surprising. We have floods. Floods are devastating because people underestimate the power of moving water. So that little logo that says, turn around, don't drown, they mean it, because a lot of these are where people are trying to drive across some flooded water and areaway. Maybe you've been down that road time and time again, but we just don't know what has happened to the road underneath all of that water. And water, very swift moving, can carry a car away, and you get in trouble really, really fast with floods, flood death. So that's averaged over 30 year. We got floods like our most devastating for fatalities in there. The 10-year average also is on the high side. And then of course, even in 2019 itself, right there, that red bar, again, floods are your major fatalities coming from the floods. So let's not ever underestimate the power of those flood waters. So weather and fatalities, we had like lightning here, tornadoes here, hurricanes, the heat-related illnesses, winter weather, cold weather, wind, rip currents. Yeah, we had a lot of deaths from rip currents in 2019 as well. So just a little bit of data there. Of course, our meteorologists are the data-hungry people and have lots of statistics on various things. So let's dive in here to chapter 14, our last chapter of the semester. Take a look at some of this weather patterns and some severe weather. So we want to really look at some of the characteristics of these air masses and what we mean by an air mass. An air mass is an immense body, immense body of air, really covering great expanses, hundreds to even thousands of miles in expanse. So these are very large air masses, perhaps several kilometers thick as well, so they can go kind of deep in there. But what they are, they have a very similar temperature and moisture content throughout that air mass, and it's really, and with altitude as well, similar moisture and temperature characteristics. And they move and they can affect a very large portion of a continent. So kind of what is your source region for your air mass, and that's going to help dictate what these characteristics are going to be, temperature and moisture characteristics. They're giving us just one example here, there are many, of a cold Canadian air mass, for example. So that's going to originate up there in Canada, right? Very cold, very dry. We're over land here. We're in a more of a polar type of a latitude, so cold, dry air mass. And you see that that can kind of retain a lot of that characteristic as it moves down and across the United States. And so well into, here we got Wichita, Kansas, Oklahoma City, Dallas, Texas, Houston, all the way on down, even down into Mexico. It can retain some pretty cold temperatures, only 10 degrees Celsius here. And it originated at like minus 46 degrees Celsius. So retaining kind of that same temperature and moisture content and bring it well down from its region, its source region. So that's just one example, the cold Canadian air mass, but we're going to be looking at several of these. So the source region is the area where that air mass is acquiring its properties. And we do classify our air masses on two criteria. One is by latitude. So, you know, is it coming from a polar region? Is it coming from a tropical region? So we have two kind of latitude bases for our source regions, and then we kind of classify them by a couple names here. The first one of a latitude source region is polar. So poles, of course, North and South Pole regions, these are going to be your high latitudes. And of course, we've learned about the Earth-Sun relationships, how the poles tend to have colder temperatures at the poles, right? Lower sun angles, fewer hours of daylight, and such. So giving them cooler temperatures there. So polar would be originating from high latitudes, north or south of the equator, and they're cold, okay? So polar is one, and they use a capital P for that. They abbreviate the P to stand for polar. So think of cold, kind of high latitude source region for polar air mass. Tropical then, so here we are, equator at 0 degrees latitude. So you gotta go north or south, kind of straddling of the equator, and we're in the tropics region. So they say capital T for tropical. These would be the lower latitudes, and of course that would be a warm characteristic, temperature characteristic for our air mass. So tropical, think of the warm, kind of, because in that region that's getting all those high sun angles, right, between the tropics of Cancer and the Tropic of Capricorn, 23.5 degrees north, 23.5 degrees south latitude. As we learned from the Earth-Sun relationships, these are going to be warm regions. So you've got your tropical, abbreviated with a T. Think of the warm sources for temperature. Okay. Then we want to look at the moisture content as the second criteria used to classify our air masses. So we use continental with a lowercase c to abbreviate for continental. Now continental, of course, is forming over the land, and this will be drier. So likely to be dry as a source region for our air mass, and that would be continental. Lowercase c, because they do use these abbreviations, so kind of make sure you've got those letters associated with them. C for continental, and think dry for continental. And the last one here, the fourth one, maritime, and they use a lowercase m for that, okay, lowercase m. Now this is going to form over water, so this would be a moist, humid air mass coming off of the water. So maritime, a lowercase m. So we've got our temperature criteria, and we've got our moisture criteria, or lack of moisture criteria, right? Two criteria that kind of define an air mass. And so we'll kind of put those together, and we'll arrive at several, like 4 basic air types, main air types. So let's put together the continental, so lowercase c, and polar region, capital P. So that's abbreviated CP, continental, polar. Continental is going to be dry over land. Polar, towards the poles, right? Higher latitudes, going to be cold. So this is going to be a dry and cold air mass for continental polar. The second one here, this is an important one here in the United States, the continental tropical, or continental polar is actually in the United States. Continental tropical is going to be dry, coming off of land, but warm, okay, tropical there. We can kind of think, I don't know, desert southwest kind of for the continental tropicals, warm and dry. Maritime polar, little m, capital P, so maritime coming off of the water, but cold. So sort of your higher latitudes, but coming off of the ocean, maritime polar. Maritime tropical, so maritime, very moist, humid air, but tropical, so more towards the lower latitudes, straddling kind of the equator there. Maritime tropical and continental polar, these are the ones that have a huge role in our weather making air masses here in the United States, especially east of the Rocky Mountains. It's continental polar and the maritime tropical that come into play for our weather masses. Okay, and we already mentioned that the continental polar is originating up there in Canada, right? And that air can make its way down. So central Canada, very dry, cold air mass coming from that location. And then of course the maritime tropical, that's down to our south, right? We've got the Gulf of Mexico. So we've got a low latitude and very humid air mass down there. So this is kind of showing where those air masses are coming from. It's a little bit color coded as far as what's cold and what's warm. They're using the blue for cold and the red here for warm. But let's look at the humidity as well. So we've got a continental tropical. So this would be dry and warm. Little c, capital T, continental tropical. So it's over land, lower latitude, so it's warm. That's kind of our desert southwest region in our, just kind of up there in the land, away from water. It's very dry and it's warm. Here's a very important air mass, the maritime tropical. So it's coming off the ocean, so it's humid. That's the maritime portion, the lowercase m. The tropical is that it is in low latitudes. Okay, so it's going to be warm in there. That's a major player here in the United States, especially east of the Rocky Mountains. That's just surging, forth and will bring that warm, moist, humid air mass. The continental polars, so up in here, a couple continental polars coming in from the land, but at high latitudes, polar latitudes. So this is dry and cold air coming in. And you can just see how these two are going to have a little clash happening between the continental polar and the maritime tropical. This is a big weather factor and players for our weather systems that we have here in the United States, especially east of the Rocky Mountains, right? Kind of east of the Rocky Mountains in there. Let's look here. Maritime tropical, again, off the Pacific as well, can come in from that location too. Now up here, maritime polar. So here we've got humid, moist air, but yet it is cooler air because it is coming from higher latitudes up in here. And that's kind of a player for our west coastal mountainous kind of regions off over there. And that can help bring in some moisture and give us some snow in the mountains up and along and through there, the Cascades, Sierra Nevada, and that sort of thing. And so maritime polar also coming off over from the north kind of Atlantic as well can bring some little weather systems off to our upper east coast as well. But big main players are the maritime tropical and the continental polar. It's especially east of the Rockies. Those are major weather players there. So maritime tropical is lowercase m, capital T, so be able to recognize what MT stands for, okay? And CP, continental polar, right? A dry, cold air mass versus a humid and warm air mass. Okay, so make sure you got at least those two abbreviations put together for classifications of our various air masses. And so they are going to kind of take us through, right, those air masses, CP and MT, continental polar and maritime tropical, kind of abbreviating them there. Are the most important air masses across North America here, especially east of the Rockies, as I've been mentioning. Continental polar coming and originating from the northern Canada region, interior of Alaska. In the wintertime, that's going to bring very cold and very dry air. Summertime, well, it's going to be bringing very cool relief to that area. So think of continental polar, very dry and cold. It is also responsible for the lake effect snows that happens across the Great Lakes region as that dry kind of polar air mass is crossing over the Great Lakes. Well, that's actually going to pick up some moisture as it goes across the lakes, and so once it's on the leeward side of those shores of our lakes, it's going to be able to produce some snow out of that. And that's sort of where that lake effect snow is happening. But that continental polar air is getting things started and bringing that air across those lakes. Really a big effect on the lake effect snows that we get across the Great Lakes. Maritime tropical, so this one is a big player as well, coming from the Gulf of Mexico. Also, we get some of that off in the Atlantic Ocean as well, but the humid, warm air mass, MT, for that abbreviation. Warm, moist, unstable air, right? The warm air is very buoyant. It wants to rise. Anytime you have lift in the atmosphere, yeah, you are going to get the precipitation to happen. So, you know, in the eastern United States, especially off over Florida. Florida has a tremendous amount of precipitation. If you remember, it's kind of in the confluence of converging winds coming off the Gulf, coming off the Atlantic Ocean, and they get that lift and that rise, that convergence of the air masses. And so very unstable, warm, moist air is the maritime tropical. So keep that in mind, MT for that abbreviation. Location here for the continental tropics, so CT. As we mentioned, the southwest of the United States, that's kind of our desert southwest region when we talked about our deserts. Mexico, again, this is going to be a very hot and dry. So temperature and moisture are the components of an air mass, right? But hot and dry. Really not too important outside of that source region, so interior of the continent kind of thing, kind of away from any access of water. You'll get that continental tropical in the low latitudes. And then there's the maritime polar, so maritime moist coming off of ocean setting, polar though, high latitudes north or south of the equator, bringing precipitation to the western mountains. So think out there on our west coast, you know, there's California, Washington, Oregon, a state, and all these places up and along through there. And occasionally, that was on the upper east coast of the United States, we can get something we call a nor'easter. They call it a northeaster, meaning it's coming from the northeast, the winds are. Very cold temperatures and snow. So cold from the polar, bringing moisture though, maritime. So that's going to kind of help with the cold temperatures and the snow, a nor'easter. Maybe you've heard of a nor'easter. But the wind's kind of coming from a northeasterly direction on towards the land from the ocean. Okay, and so those are basically the classification of our air masses, four main types to keep up with, and make sure you've got your little symbols, lowercase and then uppercase letters that depict those, okay? All right, and so let's look at fronts. So we mentioned fronts before when we talked about lift in the atmosphere, the frontal wedging, the cold air, and then the warm air wants to rise up over it. But fronts are boundaries that are going to separate air masses of different densities. And so definitely our air masses are going to have different densities. Just think about the temperature. The cold polar air masses are going to be much more dense than your dry, warmer air masses, right? So tropical versus continental, or tropical versus polar. Right away, we've got some temperature differences that are going to give us differences to our air masses as well. So cold versus the warm or the hot. So definitely, as these air masses retain their identities, the warmer, the less dense air gets forced aloft. As you remember, that's the more buoyant air. Cooler, denser air kind of acts as a wedge, and there you go. The air is going to rise. That warm air will rise. And so these are boundaries that separate the different air masses. That's called a front, okay? And of course, along a front, right, the less dense air is always going to get forced aloft, forced to rise, okay? And so in looking at these types of fronts, we talk of a warm front and a cold front, okay? And they have some little symbols that they put on a weather map for us to depict these as well, kind of coded. Like we already started looking at the isobars and the wind station plots, kind of wind direction, wind speeds. Well, they also do this for the fronts as well, to show you the location where there is a warm front or a cold front on your map. So in a warm front, the warm air is replacing cooler air. It's coming in and invading in a cooler region. Warmer air gets left behind there as it passes by. And it is shown on a map by a red semicircle. Let's see if I have something. Surely they're going to have something for us. Where that went. Maybe not, didn't bring it with me, but they'll have something for us here. I thought for sure I had mine. There it is. Found it. So something like that, for very simplified there. It's red semicircles, okay? Red semicircles on a map there. And that is saying behind that is the warm air, right? And the warm air is coming in to a region of colder air. That's a warm front depicted by red semicircles, okay? Extending off of one side of your low pressure system. It's these low pressure systems that are going to be bringing these. It has a small slope to it. Remember our gradients that we talked about, maybe 1 to 200, but this is a small slope compared to our cold front, which has the steeper slope to it. Clouds become lower as the front nears, and it's a very slow kind of rate of advancement to it. You're going to get light to moderate precipitation out of this. So it's not going to be, a real deluge or downpour or like a thunderstorm. No, you're not going to get that out of a warm front. It's going to be more light to showery, moderate precipitation. And you can kind of predict the coming of a warm front. I can get that there. As we look at this kind of progress, here's our warm air. Not too steep of a slope that it's going up. Moderate precipitation here, but kind of look at the clouds that are coming in. So if you start to notice in the sky, it'll start out, day by day kind of advancing, but the cirrus clouds, those high, thin, wispy ice crystal clouds, the cirrus clouds, you start to see the cirrus clouds really high up in the sky. And then it builds to cirrostratus clouds, right? And then later you're going to eventually, the next couple days, you're going to get the nimbostratus clouds. Those low-lying gray clouds, the stratus clouds, right, that cover the entire sky, and you get rain out of that, the nimbostratus clouds, if you remember that. So you're seeing kind of that advancement of the clouds, and so really a study of the clouds and how they're changing day by day can kind of predict what weather's coming our way. So it begins as a kind of premonition here, the cirrus clouds, then the cirrostratus, and then of course the nimbostratus. These are all kind of a series of clouds, the appearance of clouds forming that are letting us know a warm front is coming, an advance of a warm front. Really does indicate the approach of a warm front. So kind of paying attention to the clouds as they change over day by day can really help predict some of the weather coming our way. Versus here, a cold front. And so for a cold front, this is where the cold air is going to replace the warm air, right? It's barreling through. This one has a very steep gradient, twice as steep gradient, 1 to 100, than a warm front does. So a very steep gradient. The air is really going to rise steeply over it. And it's shown on a map with blue triangles. And so let me pop that under there again. Here's our low pressure system coming off the side there with blue triangles. That is indicating the front or the leading edge of the cold front. Okay, there's cold air behind here and it's leading and going in that direction. And of course in the northern hemisphere, right, our low pressure system goes in a counterclockwise direction, right? And of course the winds are converging towards the center, but this has got warmer air out behind it and it's going that way counterclockwise, colder air over here, and it's leading this way. And so in a counterclockwise motion, right, cold front there, warm front there, okay? So these are our boundaries of air masses. So when we get a clash here in, say, the United States, and this looks to be the northern part of the United States on that little map there, there's Minnesota and Wisconsin and such. So it's a clash between that maritime tropical air, that warm, moist air coming off the Gulf, working its way up, right, from across the United States there, and then the continental polar. So the cold air here coming from the north, right? A clash between those, and we're getting this low pressure system with a cold front off of one edge and a warm front coming off the other edge. But yeah, your cold front is depicted by blue triangles on a weather map, okay? And it's going, the cold front really advances faster than the warm front. This is the one that's really going to pack a punch. Is associated with more violent weather than a warm front, you know, not just the showery precipitation. Here we are getting the very dramatic, very violent cumulonimbus clouds. Our thunderstorm clouds are going to come out of this one. So intensity of the precipitation is greater, but it travels very quickly, and so the duration of the precipitation ends up being shorter in this scenario of a cold front. These are going to give you your crazy violent kind of weather can happen from these. And so weather behind the front is dominated by the cold air mass, right, behind that blue triangles, right, subsiding air, right, so sinking air, clearing conditions. So once that cold front and all the violent weather that happens along that cold front, right, the wedge that happens, the thunderstorms that happen, behind it, coming in behind it is that drier continental polar air, okay, very cold, very dense air, so you're getting subsiding air, clearing conditions. So, you know, after the cold front passes through, you get a cooling off of your weather. It's a little drier air mass, right, behind it. You're getting the clearing conditions behind a cold front. So definitely some dramatic weather that can happen, and they're depicting that here. We've got a really steep kind of cold front there. It's forcing the air That warm air is really being forced up above there, and that's where we're getting the towering cumulonimbus, a lot of lift. So you can get great vertical development of your clouds in there. That's a cumulonimbus cloud, thunderstorm cloud. So you can see the heavy precipitation here, you see the lightning, and you would definitely be hearing the thunder. And so you can actually predict and kind of estimate how far away your storm is, the main cell of your storm. So initially you would first see your lightning, because the light travels faster than sound, so you would see the lightning, and then a little bit later you get the bang. So there's a way to kind of calculate, we call it the flash to bang method. Basically, for every 5 seconds, okay, that you have to wait, you count after you see the flash. If you count 5 seconds, your storm is 1 mile away, okay? And so for every 5 seconds, that's 1 mile away. So let's say we see the flash and we start counting. And maybe we had to count about 30 seconds, okay? So if 30 seconds went by, right? 30 seconds divided by 5 seconds, 6 miles away is our storm, okay? So that lightning is actually 6 miles away. So you're waiting 30 seconds, then you finally hear the thunder. Yeah, because sound travels just a little bit slower than the light, right? Speed of light, that's faster than the speed of sound. So if you see the lightning and you count 30 seconds, you can estimate that that storm is about 6 miles away. You definitely want to be taking cover, because lightning can strike 10 miles away. So if you're within 6 miles of that, it is time to go indoors, right? When thunder roars, go indoors. That's another one of those really wise little phrases. Turn around, don't drown. But when thunder roars, go indoors, because lightning can strike 10 miles away. So certainly you're too close to that storm to be outside. So head indoors when thunder roars. So this is a cold front. You're going to get that violence, heavy precipitation. Some of these cumulonimbus storms can trigger tornadoes. Of course, you could get the hail out of this. If you remember, I talked about the hail that we talked about. Cold fronts really do pack a wallop of really some severe type of weather coming through, with thunderstorms, possible tornadoes, and some hail as well. Okay, so keep in mind those little symbols, right? With the warm front, it's these little red semicircles, and the cold front was these blue triangles on there. Of course, that's going in a counterclockwise direction around a low pressure or a cyclone system in the northern hemisphere. Okay, a stationary front. So here we've kind of stalled out, but we've got flow of air on both sides of the front, almost parallel to the line of the front, kind of going like this. The surface position of the front doesn't appear to be moving on that with a stationary front. They're just kind of parallel to one another. An occluded front, well, you get a really active cold front. Remember, they really do move quite quickly. It can actually overtake your warm front. We call that an occluded front. The cold air wedges the warm air upward. You get some complex weather. Precipitation is associated with the warm air that's getting forced aloft, but that's an occluded front. The cold front's catching up and overtaking your warm front in that situation. So yeah, you get your cold front there. It actually overtakes the warm front, and then you can get some light kind of, various kind of complex weather occurring in an occluded front. But it's basically the cold front's catching up and overtaking that warm front in an occluded front. Okay, so cold front, yeah, intensity and precipitation is greater, but yet that duration is much shorter in a cold front, but some crazy weather you can get out of those cold fronts for sure. And definitely the thunder and the lightning, right, associated with the cold front, that cumulonimbus cloud that we get. That's kind of our thunderstorm cloud. Okay, middle latitude cyclone. Okay, so this is definitely a low pressure system, and these can really take up a huge expanse of real estate. And of course, these are always going to want to be moving eastward across the United States. We have that steering mechanism, our jet stream. We have the westerlies that are the predominant, wind coming from the west, trekking across the United States. So that's kind of what's pushing our frontal kind of systems, our cyclones and our anticyclones across the United States. And so these are going to travel from the west towards the east across the United States, but it's called a middle latitude cyclone. So middle latitude just means kind of our region here in the United States, mid latitude, 30, 40 degrees north latitude. So they call it a middle latitude, and a cyclone is a low pressure system, if you remember our low pressure system talks. So definitely your first signs of their approach are going to be off in the west. So we always kind of look to the west of the United States to see what's going to be coming our way, here in Arkansas several days later. So whatever they're getting out there in the west, it's coming our way, okay? So yeah, it does kind of approach from the western sky and trek towards the east. Keep that in mind. It takes a few days, 2-4 days, to finally pass over a region. So that's sort of the trek for our middle latitude cyclones. We call those, okay? Big weather makers in the United States. Now, largest weather contrasts, of course, are going to be occurring in the spring months, because you still have, a lot of the cold air kind of coming from the north, warm air. It's a transitionary period, right? Warm air trying to come in from the south, and it mixes right here in the mid-latitudes, and spring tends to be a very contrasting weather period for us here. And you're definitely going to see changes in the weather associated with the passage of the cyclone, the mid-latitude cyclone. And the changes are going to depend on the path of the storm, but typically, once a low pressure system, the cyclone, passes through, you are going to be followed by a high pressure system. Remember how those just kind of follow one another? And so once you get the passage of the low front, or the low cyclone system, you are going to get the high pressure to kind of settle in behind that, the clearing of the skies. So they do kind of follow one another, and so the changes kind of depend on the path of the storm, though. But these are very large, as we'll see on a map here coming up. But yeah, the weather, of course, associated with the front. So the warm fronts, your clouds become lower and thicker. So remember, you kind of look for the cirrus clouds. It'd be your first indication that, hey, here we got a warm front coming in a few days. So look for the cirrus clouds, and then the cirrostratus, and then eventually your nimbostratus clouds. And so you're going to get that light, showery precipitation out of a nimbostratus cloud. And after the passage of the warm front, the winds are going to become more southerly and warmer. Where'd my little picture go? And that makes great sense, because remember, northern hemisphere, low pressure systems, or this cyclone, they're going counterclockwise, right? The winds are convergent and counterclockwise. You can kind of see our little stick figures here that indicating the direction of our winds, right? This way. And so they say with the passage of the warm front coming past your location, winds are going to start to become more southerly and warm. Makes good sense, because that's kind of the direction of the low in there. So yes, after the passage of the warm front, winds become more southerly, temperatures begin to warm. It's kind of pulling up some of that warm air with it as it's passing by. Okay? And then, well, remember, the cold front's on its way. The cold front's coming. So there, the warm air kind of came, a southerly flow, but now look, our winds are going to start to change direction. They're going to be coming from a more northerly direction as the cold front is going to pass by. So you begin to get a wall of dark clouds the towering cumulonimbus clouds when that cold front's coming near. Heavy precipitation, the hail, occasional tornadoes even can come out of those. They can get spawned out of those. We'll look at our tornadoes a little bit in just a little bit. But after the passage of the cold front, the winds become more northerly. It's a counterclockwise motion there. The winds become more northerly, the skies clear, the temperatures get colder and drop, and that makes good sense, okay? So as that cold front's coming along, right, the winds are gonna start to shift, maybe starting out from the west a little bit, then the northwest, and then from the north, right, as that passes by, it's going in that counterclockwise kind of direction there. And so here we go. Our winds are going to start to shift from the north. So yeah, that's going to be bringing in the colder air behind that cold front coming into your location. So yes, you are going to get the winds becoming more northerly. Of course, that's a cooler air mass, right, coming down from your cold front. Skies are going to begin to clear. Cooler temperatures. Temperatures will drop with the passage of the cold front. So yeah, as that's tracking along, yeah, all the way, you know, it's moving from west to east, but it's also going in a counterclockwise motion with the warm front and the cold front extending from the sides of that low pressure system. So here they have another one going across the United States. Just look how large of an expanse this is. Here it is. It's kind of a comma-shaped look to it. Low pressure center there. Counterclockwise motion. There's your warm front, and there is your cold front with the blue triangles in there. Notice what they're saying here. Behind your warm front, MT, maritime tropical air coming off from the Gulf. Look at your winds coming in this direction. Southerly kind of flow, bringing in the warm and moist maritime tropical air mass coming in. So yeah, you are going to get southerly winds as that warm front's passing by, warm, moist air. But then lo and behold, you know, a few days later, cold front makes its way in, right? Look at your winds now. They're coming more from a northerly direction. Of course, this is cold air back in behind here because it's coming from its source, CP, continental polar air, drier, colder air coming in this direction. That's its source of that air mass. And so you are getting these fronts of a warm front followed by a cold front, you know, a day or two later, followed by the cold front. You're going to start getting the cooler air behind that, the drier air behind it, the clearing skies after the passage of a cold front. But along the way, yeah, you're going to get some really kind of violent rain, thunderstorms, possibly even tornadoes out of your cold front, or showery precipitation with the passage of a warm front. So these are the cloud patterns of a typical mature middle latitude cyclone, we would call it, but it's a low pressure system. So yeah, that changes as that tracks across the United States, passes by your location. You are going to get that. Certainly, of course, with the approach of a cyclone and the passage of the cyclone, your pressure is going to begin to lower in your location. So your pressure trend would be decreasing as days went by, as this low pressure system got closer and closer to your location. So looking at the air pressure trend, that barometer trend we were looking at last time, that can tell you something about the approaching weather, right? Whether that low pressure is on its way. So that's bringing, and here is actual satellite view of the middle latitude cyclone. You can see the gorgeous, almost textbook shape there of the comma of a mid-latitude cyclone. Quite a beautiful sight there. But tremendous mileage on this, right? So it's really covering, there's Texas right there. A large portion of the United States, so hundreds to thousands of miles that these middle latitude cyclones can cover. But these are major producers of our weather across the United States. Always kind of starting out in the west and working their way toward the east. and taking several days to make it there. Right? It does take a little while to get there. Yeah, and so what's kind of happening after the passage of the fronts, that's going to kind of dictate, well, where was my source of my air? You know, was it the cold front? Going to be more northerly winds, cooler temperatures, because the north-northwest, that's going to be the direction of that counterclockwise rotation around that. Right? So convergent and counterclockwise around a cyclone. Okay. And so basically, yeah, the roll aloft there, it is going to dictate what your weather is going to be doing. You're going to get your cyclone, you're going to get your pressure to start to drop around that cyclone, but then the passage of that is followed by an anticyclone, right? They kind of feed off of each other, so they follow one another. The upper, it's generated by the upper airflow, maintained by the upper level airflow, and they're typically found adjacent to one another, kind of following one another. If you remember, convergent and then rising air, convergent counterclockwise for your low pressure, rising air. Well, what does it do when it rises? It rises and then it diverges. And so that goes over to a high pressure system next to it, adjacent to it. So yeah, they're kind of found adjacent to one another, and they kind of follow one another. You get the passage of the cyclone, and then you'll be followed by a high pressure system, you know, a day or so after that. So they do typically kind of follow one another. Okay, thunderstorms. So in looking at some of that severe weather, our thunderstorms, of course, are coming from our cumulonimbus storms, our thunderstorm clouds, we call them. Cumulonimbus. So cumulus, those globular, kind of puffy clouds, but nimbus, rain, right, for nimbo. So cumulonimbus clouds are our thunderstorm clouds. You can think of that, really associated with the cumulonimbus cloud. Heavy rainfall, we're getting the lightning out of that, right? Occasional hail, because in those very towering, vertically developed clouds like a cumulonimbus cloud, you're getting a tremendous amount of updraft and downdraft happening, bumping, right? The levels can, be freezing at the top of the cloud, liquid rain, in the middle part of the cloud, so that you can get the development of that hail. Occasionally you can get some hail out of these if they're developed tall enough to where the upper portion is actually below freezing, and you can get some hail out of that. Lots in progress at any one time, 2,000 they say at any one time, 100,000 per year in the United States of our thunderstorms, most frequent in Florida and the eastern Gulf Coast region. As we mentioned before, Florida, it is the peninsula of Florida is just in that location where you have the convergence of maritime tropical air masses, right? And they're going to converge, and you're going to get the lift, and of course that lift is going to cause the aid for a towering cumulonimbus storm. So these little thunderstorms pop up very frequently in the Florida region, most typical. Of course, in the maritime tropical air masses, that's that warm, moist air, it's going to want to rise as well. It's very buoyant, warm temperatures, less dense, going to want to rise. There's your puffy cumulus clouds. So a towering, they really will tower to great vertical heights, a cumulonimbus cloud, we would call it. And that's kind of aerial view looking down from the tops of them there. Interesting viewpoint. And here is definitely thunderstorm going on. We've got the lightning, very dangerous, right? You want to be indoors for something like this. You do not want to be caught outdoors when there's lightning going on. 10 miles away you can get struck by lightning. So that's your cumulonimbus cloud there. Tall clouds, puffy, lightning coming from them. Average number of days per year with thunderstorms. So we got a variety going on here. Just kind of looking east of the Rockies, and why that might be is because of those that clash of that maritime tropical, right? And you got the continental polar kind of clashing, creating thunderstorms. But look off over here, Florida, has the most, Florida, 100 days per year, 100 days per year where they're getting a thunderstorm. So that's a lot right in through there, and that's right where those air masses will converge coming off the Atlantic and the Gulf and will rise, and you're going to get some thunderstorms from that. So that location is a hot spot for thunderstorms. So the stages of development, of course, they're going to require the warm and moist air, so that maritime tropical air, definitely. The instability, the lift, right? We got to have the air to rise in the atmosphere so you can get the expansional cooling, right? The condensation to happen, and then of course precipitation to happen. So you're going to need high surface temperatures to allow for that, moist buoyancy happening. Most common in the afternoon and early evenings, because from the heating of the day, right? The solar radiation, the heating of the day, warming the atmosphere. So most commonly afternoon to evening, we're going to get those. Okay. But you need the shear, you need the lift, you need the instability, you need the moisture in there. Continuous supply of the warm and moist air. Each surge causes the air to rise higher and higher. You're going to get an updraft next to a downdraft. So within the vertical build, you're going to get an updraft right next to a downdraft. This is like getting towards the mature stage of your thunderstorm. You're going to get the precipitation forming, the gusty winds, right? That downdraft producing the gusty winds. Lightning, maybe some hail out of that, heavy precipitation. It almost kills itself off though, because the cooling effect of the precipitation, the evaporation of that precipitation, kind of makes it peter out and die out. So it marks the end of the thunderstorm activity. It almost kills itself as it goes because of the precipitation. So yes, this is probably they're speaking here about the mature stage of the thunderstorm development. And I think they have a diagram of that as well. So we start off with the cumulus stage. You're getting that instability, something to cause the rise to happen, the warm air, moist air rising. Then at the mature stage, so stage B here, you've got the updraft right next to the downdraft. So that gust front, that downdraft as well. Precipitation, this would be the stage you would get some hail out of that. Potentially a tornado would happen at the mature stage as well. But eventually it kind of just kills itself off. The downdraft takes over. The updraft is no longer, because it's cooling as it rains, and the evaporation of that rain, that's a cooling process, the evaporation process. So downdraft kind of takes over. You start to get the lighter rain behind that, and that's sort of the end stage, the dissipating stage, they call that, for your thunderstorm. So that's sort of the stages of a thunderstorm, and some of those can get to the severe level in there. Tornadoes. So some of those cumulonimbus clouds can give you a tornado. Okay. So this is a rotating column of air that would end up extending down to the ground. The funnel would actually extend down to the ground from the cumulonimbus cloud. It's very low pressure inside, causes the air to rush in your winds, so you're going to get your greatest wind speeds with a tornado, okay? Well over, like 310, this says 300 miles per hour. They've been clocked at 310 miles per hour. These are stronger winds than even a hurricane. So the strongest winds recorded have come from tornadoes. They produce the highest records of wind speed in a tornado. You can also get these smaller suction vortices that are inside a larger rotating funnel. So you can get several tiny ones within it as well. Quite dangerous for that. But yeah, your tornadoes have the highest wind speeds. Occurrence and development, and so average 770 each year in the United States, and I think that number has gone up. Latest, I think I had 1,300 tornadoes per year on average, so that's increasing. These PowerPoints are kind of old. Most frequent from April through June. Now, why would that be? That is because that's a transitionary period, period where we still have some cold air in there, and then we're starting to get the change of the season, right? Going from spring to summer, and then you're starting to get warmer air in there, but you're getting very contrasting air masses colliding, right? Clashing, basically. Cold continental polar air, warm, moist tropical air right over our location here in the United States. And so the months for us are April to June, where they're most frequent. However, know this, any month out of the year, we could get a tornado, okay? It's just the frequency happens most between April and June. But any month, even December, even January, we can get tornadoes here in the United States. So they are associated with the thunderstorms, so the cumulonimbus clouds. Formation, so most often occur along a cold front where you're really getting that crazy severe clash, right? The steep wedging, frontal wedging that forces the warm air to rise up over it. Great vertical development of your clouds, so a cumulonimbus cloud. So occurring most often along those crazy cold fronts associated with huge thunderstorms called supercell thunderstorms, really covering a large area there. And then it tends to, here we go, we've got some stronger winds up here, weaker winds closer to the surface because of air friction. Right, we talked about how friction slows the winds. Well, up above, those winds are going a lot faster than the winds below, and it almost starts to give this rolling kind of effect here, where the spinning along a horizontal axis, stronger winds aloft, weaker winds below, you begin to get sort of a shearing happening, a change in wind direction with height, creating a spin, definitely. And so that gets picked up right into the updraft of the thunderstorm. And yeah, here we go. We've got a huge cumulonimbus cloud. And there you go, coming out. There's just a small little funnel there. When the funnel actually does touch the ground, that's called a tornado. Okay? And so yes, the spinning of that, sort of the wind shear, is something that it does need to kind of keep that tornado going. Okay, so diameter, so they're not too wide, 500 to 2,000 feet in diameter. Speeds can, they can trek a good distance, 30 miles per hour, cover, some real estate there, spread across the landscape. Can cut about 6 mile long path, like staying on the ground for 6 miles at a time. Is possible. Sometimes they'll go down, they'll come back up, go down, come back up. So it's like some houses are spared and then others aren't in your neighborhood. But they can have been known to stay on the ground for 6 mile long path, just cutting a path of destruction through that. Maximum winds range beyond, 310 miles per hour. And so definitely your tornadoes have the highest recorded wind speeds to them. And so what they're looking at for intensity is measured by what we call the Fujita intensity scale. Get that right. I had that somewhere too. Where did that go? But it's actually been what we call an enhanced Fujita scale now. Here it is. They've replaced that by the enhanced Fujita intensity scale. And so its intensity is, they go out and kind of analyze it of what kind of damage was done. So that one is the enhanced Fujita scale, wind speed ranges. And so EF0, 65 to 85, you won't have to remember all of these wind speeds on there. But an EF1, so an enhanced Fujita 1 on the scale, it's 86 to 110 miles, right? Clear on up to an EF5 over 200. So how much over 200? I mean, that just is whatever it is, right? We've had some that were at 310 miles per hour that we've been able to record. Maybe there's been some faster ones. in there. But we actually do use the enhanced Fujita scale for that. For tornadoes, okay, the enhanced Fujita scale. And as I mentioned, the time frame here in the United States is usually April to June. They've got the letters of the month here. Any day of any month of the year, we can get tornadoes. It's not down to zero for any month. But kind of our maximum days is between April and June, where we have most of that clash of the continental polar and maritime tropical air masses clashing. But over in Oklahoma, they just seem to be in a region where it's a hot spot for tornadoes. Over here in Oklahoma, they tend to get the most tornadoes in the United States. So yes, keep that one in mind. Oklahoma is our main place that does get all of those tornadoes. It's just a confluence right in the region where the cold air and the warmer air would be clashing in through there. And typically ours are going to trek from a southwest to a northeast kind of a pattern. Our tornadoes would. They go kind of start out in the south west and go towards the northeast. They kind of cut a path like that and would track that way across the United States, southwest towards the northeast. And that's just the direction that the storm system would be taking them. So these can be very difficult to forecast. They're getting better and better at it, looking at different debris signatures to know when there's been a touchdown by radar. Really, we rely a lot on our storm spotters. So they go out and they actually do us it's dangerous work, but they really do help us to actually spot the tornadoes. So observations from people. But we also do rely on our Doppler radar highly in order to kind of predict these and track these. That's the primary warning system. But very difficult to forecast. But a tornado watch, we want to alert the public to the possibilities. So they have found, our meteorologists have been, keeping track of the atmosphere continuously, and they're seeing some ingredients come together. They're seeing the air masses. Right? They're tracking the air masses, they're plotting the cold fronts and the warm fronts, and they're seeing the potential for the ingredients to come together, right? So they are going to alert the public to the possibility. And so this would be kind of a broad area, right? 25,000 square miles, issued when conditions seem like, let's just have a heads up here, let's be paying attention. It could happen. So that's kind of a watch. That's kind of a broader area, expansive area. But a tornado warning is going to be a much smaller kind of region than a tornado warning will pop up. But it has either been cited by people out there, our storm chasers, or indicated by the weather radar. So Doppler radar is something we really rely on. It will help to increase the accuracy by detecting the air motion. So we kind of put that in the velocity mode, and we can tell, which way the winds are coming, toward or away from our radar. The intensity of the precipitation can give us some clues as well. Any rotation we start to see, they can detect that by the Doppler radar. Now they can't necessarily tell if it's on the ground or not, because sometimes the radars are pointed up, mid-level in the atmosphere. So they aren't always sure that it's actually touching the ground as a tornado, but they're seeing the rotation and that potential that, hey, this one, if it does touch ground, is going to be a tornado. So really our warning system comes from the observers out there and this Doppler radar really helping us today in our warning systems. Okay, so that's the tornadoes, very, violent weather. Now we're going to continue here and look at hurricanes, okay? Hurricanes, these are the tropical cyclones, right? So most violent storms on Earth, to be called a hurricane, you've got to have a few criteria that need to be met, and that is that you have winds in excess of 74 miles per hour. Once that gets to 74 miles per hour, of course, they're going to give it a name. They name our hurricanes now. And it is a cyclonic circulation that begins out over the water. Okay, so a hurricane. Now, our hurricanes are going to form between the latitudes of 5 degrees and 20 degrees either side of the north or south of the equator. The reason they don't develop along the equator, if you remember, we talked about the Coriolis effect, right? Things that veer to the right in the northern hemisphere cause it to veer to the left in the southern hemisphere. Well, right at the equator, we don't have the Coriolis effect. Remember that? So 5 degrees north or south of the equator, we're really not getting the Coriolis effect. It's too weak. So you're not going to see your hurricanes develop there, okay? But 5 degrees latitude, north or south, up to about 20 degrees north or south latitude, you're going to need waters to be warm enough. You need waters almost 80 degrees Fahrenheit. And so if you go too much further than 20 degrees north or south latitude, your waters are not going to be hot enough to spawn these hurricanes. Okay, so basically they're going to originate, I think I had my book somewhere, between 5 and 20 degrees north or south latitude. Okay, I have that somewhere in here, yeah. So this is out of your book, page 436, figure 1427. So hurricanes do not develop within about 5 degrees of the equator because the Coriolis effect related to the rotation that gives the storm their spin is too weak along through there. So we're not going to see them along the equator, right? Now the ones that affect us here in the United States, they're actually going to be starting off here on the west coast of Africa. These little low pressure cells that come off of the kind of west coast of Africa, they begin out over the water, and then of course the winds, remember the trade winds that come along, the trade winds, and will bring them our way over here to the United States. So most of our hurricanes kind of begin out here, mid to late summer, right? When the water has had enough time to warm up. Remember the moderation of water? It takes it a little bit of time. It takes a bit of a lag for the temperatures of the water to finally warm up from all that high solar angles from the summertime. So late summer, those low pressure systems coming off the west coast of Africa being brought by the trade winds, that's what's bringing in those low pressure systems rotating counterclockwise in the northern hemisphere, clockwise in the southern hemisphere, of what we do call hurricanes. So those do form and develop. Most of those will originate off of the coast of Africa, right, in late summer, and then kind of come our way. But yeah, definitely not going to see them within 5 degrees of the equator because of the lack of the Coriolis effect. Remember, we got to get the rotation going by the Coriolis force in there. Okay, and we do need those tropical kind of waters, the warm, about 80 degrees in there. And so once your winds do get to about 74 miles per hour, we got a hurricane. We're getting a name out of this as well. So again, forming between 5 and 20 degrees north and south latitude, those tropical waters. And we kind of give them various names depending on, you know, kind of the location gives them different names. Typhoons out there in the western Pacific, cyclones in India, in the Indian Ocean. Of course, the North Pacific has the greatest number per year. So let's kind of look at the parts of a hurricane. The eye wall, okay, just around that center of low pressure, right? The eye wall, right around in there. It's very near the center we've got some rising air in the eye wall. This very dangerous part of the storm is the eye wall. Very intense convective activity. So you've got a lot of thunderstorms happening, possibly even some tornadoes getting spawned out of some of those as well. But of course, over the water, it's not a hurricane unless it hits land, sort of thing. A wall of cumulonimbus clouds. This is still the eye wall. Greatest wind speeds are going to be there, heaviest rainfall, everything you would expect from a cumulonimbus cloud. That's in the eye wall of your thunderstorm, or I'm sorry, your hurricane, which is a thunderstorm, but in the eye wall, very dangerous location when the eye wall passes by your location. But kind of contrasting, very contrasting of that is the actual eye at the very center of your hurricane. Here, the precipitation ceases, the winds subside, or is actually very calm in the eye of the hurricane. This is where a lot of the airplanes that are trying to track your thunderstorm or your hurricane go and fly in the eye of the hurricane because the winds are calm, there's sinking air, subsiding air right at the center. Winds are subsiding. We have subsiding air, sinking air. What did we learn about that? Gradually descends and heats adiabatically by compression, compressional warming, right? It's going to dry up the clouds in that region. So, and it's the warmest part of the storm, but it's clear skies. It's very strange in the eye of the hurricane. The eye wall is this terrible, ferocious storm, high winds, thunderstorms, tornadoes, but right in the eye is very calm at the center of your hurricane. Sinking air and compression and warming is happening in the eye of the hurricane. So here we go. We've got the cross section of the hurricane. Your eye wall, out and around the eye wall in there, rotating around, right? Crazy cumulonimbus clouds in through there, but right in the eye, you're getting the sinking air, calm winds in there, no precipitation. It's very unusual, very strange of the cross section of this, right? The eye wall is tremendous, violence, and then in the calm in the center there, no wind, little to very no wind in there in the eye. Okay. So in looking at the wind speeds, right? So your hurricanes are not going to be as fast as your thunderstorms. Only about 186 miles, we would say. They got it in kilometers here. 186 miles per hour for our hurricane wind speeds, kind of clock the highest there. 310 in our tornadoes, if you remember that. But it can generate 50-foot waves at sea. So as that wind is pushing all those waves, right, all that water towards shore, to the shoreline, remember how the wavelength or the wave height builds as you get closer and closer to the shore. So you can generate 50-foot sea waves with your hurricane pushing all that water. So of course this is going to form in tropical waters. We don't really see it in the South Atlantic or the Eastern South Pacific. Sometimes those waters are, with the cold currents, we don't always get the warm enough waters in those locations. Eastern South Pacific, Eastern South Pacific, that's kind of where the cold Canary current is going. So you don't always get the warm enough of the water temperatures in there. So energy, of course, is coming from the condensation of water, that release of latent heat. So when you get water vapor condensing, if you remember, that condensation is going to release 600 calories, right? It releases the latent heat. So that's what's kind of spawning the energy for our hurricanes. It's coming from the condensing of water vapor, often, as we mentioned before, developing in the late summer when your water temperature is the warmest, providing the energy and the moisture to sustain your hurricane. Now, a little tropical depression, the winds are only at about 38 miles per hour. Tropical storm between 38 and 74, right? And so they'll give it a name, tropical storm. Once it gets to that point, they're going to name it. And then 75 miles or over 74 miles per hour, we get our hurricane out of that. And we do use maximum sustained wind speeds to kind of categorize these, but they will diminish in intensity as they're moving to either cooler ocean. So as their water source, their energy source kind of dies down when they're going over cooler water, so they'll begin to die down. Or if they move over land, again, they're losing the warm, moist air. They're also hitting friction when they hit land, so that's going to slow things down. It's going to start to tear them apart. So moving over land, moving over cooler ocean waters, that's going to start to dissipate these, or large-scale flow aloft is unfavorable. If you have too much wind shear aloft, meaning changing of wind with height, wind direction with height, that can tend to unravel a hurricane. It kind of helps feed a tornado, but it breaks down a hurricane. And so any of those things will help to diminish the intensity, your loss of your warm, moist water, or you're hitting friction over land. So now, factors that affect the amount of hurricane damage, well, your storm surge, your strength of your storm surge, that's sort of the most important factor, the strength of the storm. How far can it go inland? And you can get tremendous flooding events with the precipitation. So inland flooding is really, and remember, flooding is our largest fatality from weather hazards, right? So just how far in, that does go inland, that's important. Size and population density. So of course, how populated is the area to be affecting people. And the shape of the bottom near the shore. So the ocean bottom, your seafloor. So do you have a steep kind of slope, or, is it more flat-lying basin, your ocean bottom? So these factors can affect how it comes onto shore, how much water it's going to bring to the shore. And honestly, it's about that north kind of east quadrant where the wind plus the storm surge is going to be the worst location as that hurricane is coming on to the shore. Northeast kind of quadrant is going to get the most damage out of that, because you get the winds coming on shore and the storm surge as well. So the Saffir-Simpson scale is what we use to rank the relative intensities of our hurricanes, and I had that somewhere. Keep putting stuff in different locations. Here it is. So the bottom scale down here, again, you don't need to remember all of these, but the bottom scale is for our hurricanes, the Saffir-Simpson hurricane wind scale, and this is based on maximum sustained wind speeds. Maximum sustained wind speeds. So, a category 1 is between 74 and 95 miles per hour. 2, you're going to get some damage potential, moderate, so 96 to 110, right? Oh, up here for catastrophic, a category 5, 157 miles per hour or greater, right? I think the highest has been about 186 miles per hour out of our hurricanes. So based on maximum sustained wind speed, and that's the Saffir-Simpson scale, hurricanes are classified according to intensity on that particular scale. So kind of have your two scales, one for hurricanes, one for tornadoes, so make sure you know which goes to which on that. Just the basic, you don't have to memorize any of those wind speeds, but just how it's based on maximum wind speeds in general for the Saffir-Simpson scale. That's what we do our hurricanes for. Okay. See, I think we're almost got it here. Yeah, the storm surge, very dangerous. So that's basically a large dome of water right? 40 to 50 miles wide, sweeping across the coast. When the eye kind of hits landfall, you're going to get wind damage, the inland flooding from the torrential rains. You can get tornadoes spawned inland as well, but flooding is probably your worst damage, and again, causing the most deaths statistically from hurricanes. Okay. On that, so bad news there with these hurricane destruction. Okay, so that does conclude our weather patterns and severe weather, chapter 14, and it actually does conclude the course. So hopefully this has given you a better understanding of the Earth as a system. So we do have the geosphere, the atmosphere, the hydrosphere, including the ocean, and of course us, the biosphere. And if you get a change in any one of those spheres, you can see how it will affect the other spheres. And so always think of Earth as a system with these spheres interacting. So it has certainly been my pleasure working with you this semester. And if you have any questions, make sure that you do get with me. And thank you so much. Bye-bye.